Oh, I'm on 4.3 and I need help on number 3.
Number 3. Okay, sure. Let's see where we are. 4.3. Let's see. The PowerPoint. Let's see what this is, though. Okay, here we are. So in this section, we're starting to talk about conditional probability and complements and different things like that. So 35% of adults who own cell phones use their phones to send and receive text messages. Choose 4 cell phone owners at random. What is the probability that none of them use their cell phones for texting? Okay, so tell me kind of what was going on for you when you were trying to do this, because you always have good thought processes. I'd like to hear what.
Well, I was just I was trying to determine if it was dependent or independent, and it looks like it's independent, I think, but
They are.
okay.
Mm-hmm.
So I know that what I did, I tried to do the equation that I did for number 2, but it wasn't working out. So I was like,
Okay, so tell me what you think you should do for the third one in terms of an equation. What should I do there?
well, I know I don't know if this applies, but we have a given. The given is 35%.
Well, you have a given percentage. That's true. So now that's the percentage of people who actually use their phones, right? To
Yeah.
send and receive messages,
Yes.
right? And it's asking us the probability that nobody does that, right? So
Yeah.
whenever you're doing these, I mean, you have everything you're thinking so far is on the right track. You just need one more piece of information, right? If if nobody uses their cell phone, which is what this is, you want 4 people who do not use their cell phone to send and receive messages. If I know 35% of them do, what percentage of them don't do that?
The other
The complement of that.
the 55%. Hold on.
Yeah, you're on the right track. You're on the right track. So this is going to be.
Okay, so it would be like the other 65%.
Yeah, that's called the complement of that. So just to get you up to speed here, because you're, like I said, you're really close to the answer. So we know that here, and I'll talk a little more about independence and not, because that is a little tricky to determine. And so the more you see it, the better it is. But here we know that 35%, so I'm going to write this as a decimal, 35% of people use their phones to send and receive messages. Right? Now, the word that you were looking for earlier was the complement, okay?
Yeah.
So 1 minus, and I'm going to use 1 because I'm using the decimal here. 1 minus 0.35. Either they use it for messages or they don't. So this, you're right, this complement is 0.65. Okay. This is the probability. Okay. This is the probability that one person does not use a phone to send and receive messages, right? Now, okay, so now we want 4 people, right?
Yeah.
We want 4 of these people. So we want 4 of these 65%. And since they're all independent of each other, now how do I know that? Because you were right, but you weren't sure. What made you think they were independent?
Because the 4 is chosen at randomly and it's not chosen from the 35%.
That's half
Well,
correct. That's
kind
half. Okay. Talk to me.
it's like because I figured out I don't know how to explain it.
That's okay. But you're right. Essentially, the way to kind of think about it without overthinking it is to ask yourself this. Let's say that you and I are in this experiment. Let's say there's two of us, right?
Mm.
And there's a 65% chance that I don't use my phone to send and receive text messages, right?
Mm.
Now, if we're not related to each other, if there's no reason why my phone use should affect your phone use,
Mm-hmm.
then that's going to be independent in every case, right?
Yeah.
Now, in a situation where maybe you have a married couple and they're choosing the same phone plan, maybe then you have some dependence going on. But in general, part of it is the fact that it's random, and part of it is the fact that when you're trying to figure out, now there's other ways to do this, there's mathematical ways to do this, but if you want to know if two events are independent or not, so if you want to know if two events are independent, one of the things you can do is ask yourself this question. You can say, does the likelihood of the first person or the first object, does the likelihood of the first person, in this case, sending and receiving messages, make it more or less likely that somebody else does? In other words, does my behavior in this case affect somebody else?
Mm-hmm.
Probably not, right? Because these people are chosen at random. We have no indication that they know each other. So if the answer is no, then you have independent events on your hands.
Mm-hmm.
Okay, so these are independent. Now, more importantly, how do we calculate it? Well, since they're all independent, all you're going to do is multiply these probabilities together because they're not going to change, right?
Mm-hmm.
And there's going to be 4 of them, so you're going to get the probability of no one using their phone for messages is going to be equal to
65 to the power of 4.
65 to the power of 4. Very good. Yeah, don't
So
forget.
yeah, because basically I would, because what I would, when I saw the 35%, I was like, I feel like I should find the complement for that, but I'm not sure.
Okay, the reason that you do is there's a couple of things you can do here. You can say, well, if I go back to the problem, and this is something that this is where everything means something and it gets really annoying. Because it says 35% use their phones to send and receive messages.
Yeah.
So the probability that a person actually does use it for that is 35%. But here it says, what is the probability that nobody uses their phone for that? So all 4 of them do not use that. Okay, so another way to ask this question on the screen is to say, what is the probability that all 4 of these people do not use their phones for text? And that's why that works, okay? How about number 4?
I'm gonna try that on my own.
Okay, all right. be careful. It's the same kind of deal here. Pay attention to what group you're looking for.
Okay.
Okay. And I'm going to turn on captions because I'm not sure they're on yet. So let me, oh yeah, I'm on there. There we go.
I have a question for letter C on number 4.
Sure. At least one of the three.
Just for like clarification,
Mhm.
so since it says if at least one of the 3 households had cable TV, would I do 86 to the power of 1, 2, and 3 and then add them?
Okay, there's a couple ways to do this. That's the hard way.
Oh,
So if you have, now you can lay this out in a tree diagram or put the probabilities together. But one of the things that we really emphasize a lot is the idea of the probability of at least one fill in the blank, right? Whatever that is, at least one whatever, right? Is 1 minus the probability that nobody does that.
uh-huh.
So the easiest way to approach this is if you have a probability that says, we're looking for, Jason, we're working on 4.3, number 4C right now, just for reference. In 2006, it says 86% of the households had cable TV. So we're looking for at least one of the three had cable. So in this case, when we go back, we're looking for 1 minus the probability that nobody had cable. And that the reason for that is that when you do the tree diagram, you'll see that the only option that we're not using when we use at least one is that nobody did that.
Mm-hmm.
Okay, so here you're gonna have, this is gonna equal, and we know that, let's do our complement so we can be complete. So the probability of having cable, the probability that I have cable, if I'm one person or one family, is 0.86, right? Because they
Yes.
gave that to me. And so the probability that I do not have cable is then the complement of that event, which is 1 minus
0.14.
0. Yes, which is 0.14. So now, so this becomes the probability that at least one has cable, probability of at least one with cable, whoops, at least one with cable is going to equal 1 minus the probability that all three of them do not have cable, right? So they do not have cable. That means you have 0.14, because again, we use the complement there, and we're raising it to the third power. Nobody has cable. That's the fastest way of doing it. Okay. Not the only way. You could add up exactly 1, exactly 2, and exactly 3, and then subtract. You could do that, but it's easier to do it this way.
Okay.
This is force. Just a heads up, number 6 is quite a problem on this page. So and
Thanks
if
for
you want,
the warning. I said thanks for the warning.
I can go over it if you want, but it's also its own video. I made it this morning. So so we can go over it, we can beat it to death, and then you can watch it if you want. But I tried to head it off at the, because that it is quite a problem. That problem is quite quite a thought. It'll grind on you for a bit. So how can I help you, Jason?
I had a question about 3.2.
3.2 or 4.2?
Oh, 4.2, sorry.
4.2. No, you could have a question about 3.2, but I suspected it probably wasn't that. Let's see.
It was 4.2.
All right, let me pull it up.
Did we do number 7?
Good question. I believe so, but let me, I've done quite a few, so I don't know if, no, we actually didn't do this one. I didn't do
Okay.
this one with you, so we haven't done it. You and
All
I
right.
have not done it. That I remember, but we did a lot of problems that day. All right, let me share this. so that we can see the screen. Number 7. Okay, so according to the Bureau, this is number 7 from the section prior, Giovanna, so don't get confused, okay?
Mhm.
According to the Bureau of the Census, the following statistics derive, okay, be careful of this, the number in thousands, we're back to that, of young adults living at home in a dormitory in the, or in a dormitory in the year 2004. Choose one student at random, and it says, find the probability that the student is. Okay, so here, remember what you can go ahead and add these up just as they are, and then multiply by 1,000 later if you need to. But these are in thousands, so be aware of that.
So
Have
the
you
total.
added up the totals yet?
Hold on. For ages 18 to 24, I got 13,695.
Okay, so this is 13,695. Is that what you said?
Yes.
And then for the 25 to 34 age group, what did you get for that?
Hold on. I'm writing it down.
So we have
Okay. I got 3,529.
this is 3,529. Okay. How about the row totals? The males are how many?
Uh, 79.
7,922
Mhm.
and 2,534.
I got 10,446.
10,446. Okay. How about the female?
And for females, I'm getting 6,774.
6,774. Okay. Now, we know what we have to do at the end. We have to add them up and make sure that they add up to the same. So go ahead and add that for me, so we can find the total in the sample space.
Okay. Total males. The total males and total females?
Yeah, you could either add the row totals or you could add the column totals. They should come out the same. So either 10,446 plus 6,774 or 13,695 plus 3,529. They should give you the same thing if we got it correct.
Mine's off a little.
Okay, let me see if I get the same numbers you do. So we have 7,000. Hold on, 7,922 plus 2,534 10,400. Okay, this is, I have 10,400. This is, let me erase this. This one is 10,456. Maybe that's 10,456 I'm getting.
I
And
got that.
this is 5779. Let's see, 5779 plus 995, 6,000. Oops, I think I had that. 6,774. Let's cross check this arithmetic now and see. 10,456 plus 6,774 is 17,200. Oops. 230. Now let me just check that with the other number. 13,695 plus 3,529. Okay, now it looks like it, 6, did I mess this up? 6, this is 4, this is 10. So we have 13,000. Let's see, let me add up the columns. 7,922 plus 5,779 is 13,000. Okay, this is 13. I have 13, this number here. Let's see. This number here is, I'm getting 13,701.
701.
Yeah,
Me too.
that
Was probably it.
this is 13,701. So this is 13,701. Now I think it'll match for you.
It
13.
matches.
All right, so now we're there, right? So now,
Yep.
now to the really important part. Now that we've got all that filled in, right? Let's see if we can actually find the probabilities, okay? So a female student aged 25 to 34. So where are our female students who are 25 to 34? Where are they?
995.
That's this, right? And it doesn't say, it's not giving us any restrictions or anything, so it's out of the total. Okay. It's out of the total number of people in the sample. All right. So this is going to be 9 divided by 17.
Wait, what? Divided by 17.
17,230, right?
Uh-huh.
And that I'm getting, I don't know how many decimal places. I have 0.5775 is what I'm getting for that. Right?
57.75.
I'm getting this. I'm getting, let me put it on the screen. I'm getting 50, it would be 57.75 if I have to round it to 4 decimal places.
Oh, I got it.
Okay.
Mhm.
And again,
Wait. Hold on. I got 0.0058 on the answer key.
Okay, now remember the reason for that is that these are in thousands, remember?
Mm-hmm.
So if you take, this is in, now did you use the numbers here? Or did you multiply by 1,000 first?
I multiplied by 1,000.
Okay, so that would have been, you would have had 995,000, right?
Mm-hmm.
Divided by 1,723,000, 17 million here. So this is going to be smaller because you end up multiplying. So this part is going to be, so if you want, you can do that either way, either before or after the but you have to do that part, but that's where your numbers come from. Okay, because these are individual people. Okay,
Mm-hmm.
so that's where that's coming from when you do that. Why don't you work on B? And then I'm gonna help Giovanna with another problem from 4.3 and I'll come back, okay?
All right.
Did you still have questions about this one?
No.
Are you sure?
Yeah, it's just that the answer keys different or something.
Okay, let me check it. Let me see what's going on with that. Giovanna, I see your message. I'll take care of it, okay? Just give
Okay.
me a minute here to finish. Okay, let's take a look. Maybe I'm missing something, but I don't know. Let me take a peek. Mouse cursor. Let's see. So this, take a stroll down here. What number are we on? We're doing number 7, right? 0.058. Okay, so this, all right, so these are, here's the thing. These are in thousands of people, right? So this means that, let me get my numbers lined up. There we go. Okay, so we're here, right? And we're roughly right about there. Come on, people. Okay, there we go. Something like that, right? So these are in thousands. Now it says choose one. Choose one student. So this represents this 7,922. This represents this many people. Okay, this represents 7,922,000. This represents this many people. So this total represents this many people. And this total represents this many. And this total represents this many. So I can go and I can add 3 zeros because I'm in thousands to everybody, okay? So that means that this probability, if you do this in individual people, is going to be, it says female, age 25 to 34. So we know that's this number. So we're actually doing 2,534. And then you're putting 1,000 there. That's how many females age 25 to 34 there are out of 1,732,000 with 3 zeros.
Don't you mean 137?
One, is it 137 or 1,723? Huh?
Hold on.
I have 1,723 for that. That's the 1,723 is the total of the total sample space,
Oh, okay.
right? So it's this number here. Let me erase this. Not that. Let me see if I can erase this red line without making it go away. Okay. It's this number. Okay. This 2534 over the whole thing at the bottom. Because this, you essentially divided this now by 1,000 when you did that. So move this percentage over when you did that. 2,5. So this is, let me see if I can. Do I have my calculator up? No. I don't, but if I do have it, this is going to be 2,534. 1, 2, 3. And then we divide it by 1,732. 1,732, 1, 2, 3. And 172, oops, 1,723, 2, 3. Okay, I think we're there. And that should give me second. Yeah, okay. So I'm getting let me see if that works. Let me check the other answer and I'll come back to you. Okay. Let me see what Giovanna's up to with her question, and then I'll check Professor Nickdell's solution for you, Jason, and see if it matches. If not, it might be a mistake in the key. I'll look. Okay.
All right.
I'll take a look at it. All right, so now 4.2. Right, so here
4.3.
you're in, okay, you're in for point. Yeah, you did tell me that. Thank you for the pickup there. Number 5?
Yep.
4 cards are drawn from a deck. Okay, this is a good question because this is the first time. Did she put up the other example that she was going to put up about without replacement? Because there wasn't one like this in the slides.
Let
Did she revise it and put it in?
me check.
I was just wondering because somebody had asked.
I don't.
You're not sure? Okay, no worries. It says 4 cards are drawn from a deck without replacement. Okay.
Mhm.
Now, without replacement means that I draw the card
Yep.
and I don't put it back. So something interesting happens when we do that. Okay. These are not independent now.
Yeah, they're dependent.
They become dependent. Exactly. So the easiest way to approach this, are you working on A or what? Which part are you
I'm
working on?
A.
You're working on A? Okay. Do you know how many kings there are?
There are 4 kings.
There are 4, right? And do you know how many cards are in the deck?
52.
Very good. There are 52. So before I draw the first card, what is the probability that the first card is going to be a king?
4 out of 52.
4 out of 52. Now, just for this particular part, I'm going to suggest that you not reduce this immediately because I want to show you something.
Mhm.
That's harder to see if you reduce it immediately. Okay. I'm going to show you what happens here. So this question is, let me figure out where I'm at. Okay. So we're drawing 4. Okay. So here we have 4 of these, 4 kings, right?
Mhm.
And we're not replacing it. So the first king, we have a probability of 4 out of 52, right?
Yeah.
Now, if you draw a king the first time, right? How many kings are left in the deck?
If I draw 1 king the first time, there will be 3 kings left.
Right. Think of it as sequential draws. That's the easiest way. If you try to think about it in terms of 4 cards at once, that's harder to do. Yeah.
Yeah.
So there'll be 3 kings left, right? And how many cards will be in the deck?
51.
51. That's why this becomes dependent. You see?
Yeah.
Now, how about the third king? When we get to the third king, right? How many cards, how many kings are in the deck now?
1. Oh, no, 2.
Not yet. There's, yeah, just before you draw, there's 2 left, right? So there's 2 here. And how many cards in the deck? You've drawn 2 out. You're about to draw the third one. So there's 50 cards in the deck, right?
Yeah.
And by the time you get to the last king, king number 4 king, this is your 4th king, right?
Mhm.
This is 1, because now there's 1 king left and there's only how many cards? 49 left in the deck.
Yeah.
Okay, so in this case, there's 4 probabilities and they're not the same. So you're going to multiply these two. Now you can reduce these fractions, 3 of them, and make it a little bit easier. But I wanted you to see how this works. Now, if my cards had been replaced instead, okay, if I had drawn the first card and put it back, it would have been 4 out of 52 every time.
Mhm.
Okay, that's the difference. But the reason that I wanted you to leave it this way is so that you can see how this changes.
Yeah.
Because this is a very common pattern, and it's not just in this pattern of taking 1 off. Sometimes we take 1 off of both the numerator and the denominator. Sometimes we take 1 off just the numerator. But this pattern is very common, and it's a pattern that's going to come back in other problems that we do. So part A looks like this.
Mhm.
Okay. Tell me if your answer matches the key, just out of curiosity, Giovanna, just because I don't know if that's, I'm going to check her key for the other problem and see if See if we
Okay.
found an error that.
Let me multiply it first.
Yeah, take your time. No worries. I'm gonna check this while I'm here and see if we managed, because we thought we had found it, but you know.
Teacher.
Let's see, Gmail.
Why?
4.2. You're working on 4. Let me check. 2. Okay. Here it is. Let's check her answer key, and that's number 7. I think it's this one here. No, we did that one. We did that one too. Did I get this wrong? 17,320. Let me see. Let me make sure I got the numbers correct. That looks good. 13,700. Okay, so this was 995,000 divided by 17. No, you know what? Okay, let me put this up on the screen for you. Jason, I
Can
put
you
it.
so do I multiply all the fractions together, right?
Yeah. Mhm.
And I know I'm supposed to reduce it. I got 24 out of 6 million something.
Oh, Lord. Okay. Do you know how to make your calculator? Did it not reduce it for you?
It wouldn't reduce it for me.
It wouldn't go and reduce it for you?
Yeah.
Ew. Okay, well, all right, give me a second, because give me 1 second here to come back. Jason, we have all the right numbers. I had an error when I put it in the calculator. Okay.
Oh.
So I gave you the wrong. Let me show you what this look. You're fine, Giovanna. But on
Okay.
Jason's problem here, this is what your numbers look like. Okay. So we have all the right numbers here. Okay. Now you can, because you're doing this, you can either do this as 1,000, or you can do this with 1,000s here. It's not going to make a difference. But I had left off a 0 when I put this in. So, and I didn't do it on the screen, so that's my fault. But here's your table. Okay. So there's your numbers. These numbers all match. The numbers at the top all match. But this decimal comes out to 0.0577.
Where did 199 come from?
199. This should be, that was what happened when she reduced this fraction. 995 over 17,230.
Mm-hmm.
That reduces to this number here. Okay.
I don't get it.
The fraction 900. Okay, so it should reduce it for you. Let me see. Because sometimes the calculator is fickle. So let's put the calculator on the screen. Then I can show you what's going on with yours also. Because most of the time it will do it. Occasionally you have to kind of coax it into good behavior. So if we're looking at this, Oops, no, I don't want to create a poll. I want to share the calculator screen. But first I want to go back. Okay, so this is your, oops, wrong assignment. 4.2. Okay, here it is. 4.2. This is 4.3. So hold on. I need the number again. Give me a minute because I've got too many windows open. This is, let me check something. This is 4.2. 4.2. This is this. Okay, so we're going to do, okay. So we have 2,534. So this is going to be 2,534. And we're going to divide that by our total, which is, so we're going to go here.
I
gonna-
can't see. You're
I'm
not
going to,
showing-
I know, I'm bringing it up right now. Give me a minute. I just had to get the number in the screen. Let me see if it will cooperate with me. There we go. Okay, now you should be able to see it.
All right.
2,534, right?
Yes.
And we're dividing by what? 1,000, was it 17,000 something? 17,000. 230, right? Is that what we
320.
were? 320, okay. Let me fix that. Are we good here?
Yes.
Now, sometimes what happens, and maybe the same thing happened to you, sometimes what happens when you convert to frac, it's too big for it to convert it. So let's see what happens here. Okay, now here it converted, but it didn't convert all the way, okay? So this is where 2,534 over the total is where this, so if this doesn't, sometimes it doesn't, and sometimes you have to reduce it manually, but this is where I'm gonna have Professor Nickdell look at this because I don't know that this is the right answer to that. So you know what, skip that part of the question and I'll come back to it. Jason, I'm gonna text her right now and ask her about it because I think that's a mistake. But maybe I'm missing something. Okay. So don't stress over that. I'm gonna help you figure that out. But just, was that the only one from that section that you were stuck on?
Yeah.
Yeah. Okay. Give it a few minutes. I'm gonna message her. But let me help Giovanna. What was your fraction that you were trying to reduce? Oh, you were doing the 4, right?
Number 4.3.
So you are doing this one, 4 out of 52, right?
Mm-hmm. 52.
Now, my suggestion here, okay, once you've done this here,
Mm-hmm.
because of the fact, and sometimes this happens, and this is a good practice. Like I said, the only reason I had you do it this way is so you could see the pattern.
Yeah.
Because I wanted to point that out because I don't think it's been emphasized. So you're not the only person with this question. But if you do this, you get that ugly thing there.
Yeah.
And if you go, which granted, that's an ugly monster there. So if you go math, convert to frac, whoops, math convert to frac, it's not going to help you much. What
Yeah.
I would suggest that you do in that case is re-enter this, but try and reduce each of the individual fractions.
That's what I did, but I still got the same answer.
It still came out the same.
Yeah.
Okay. If it does, usually what happens in a case like that, if it doesn't reduce, then she's not going to make you reduce it by hand. But what you could do, and if it's a test, she's probably not gonna give this to you this way. Because if it gives you an answer like that in the calculator, then we're, it's not going to be worth your time to go in work that out. But you could go ahead, and since these are all ones at the top, you see,
Yeah.
you could
But I
just
do multiply all the
you
denominators
could
and
just
numerators.
multiply the denominators and reduce the fraction that way.
Yeah.
Okay, but she's not gonna make you, if the calculator doesn't reduce it for you, she's not gonna make you do that manually. You can just report but do be aware, and this is a good teaching practice for this. Do be aware that if you saw this answer, okay, this is your answer, but do be aware that this is your decimal places. So this probability is really 0.00000369. It's 6 more decimal places to the left.
Yeah.
Okay, so be careful of that. Your probability is not 3.69. Okay, but that's how I would do it.
Okay.
All right.
I'll try the other one. I'll try the other letters.
Yeah,
online.
feel free to stick around. I knew this section was going to be sticky. So let me just text her while I'm here. And see what I'm missing, because I 4.2, and we're looking at A, right? Okay. 1971. Let's see. I'm gonna see about this and see if she's available. Let's see if she's available. Close. Okay, let's see if she's available. Hop in real quick. See if she responds. Let's do it. I'm gonna mute my mic for a minute, and I'll be right back.
For number 5, is there a shorter way to do it? Because I have to find diamonds, I have so many fractions. Oh, you're muted. I can't hear you. Hold on, let me. I still can't hear you. You're muted. Your microphone is muted.
I said I was communicating with the professor. That's why.
Oh, okay.
But I have news for both of you, okay?
What is?
So if your calculator won't do that, like if you get a big fraction like that and it doesn't reduce it, like don't worry about giving her the reduced fraction in a case like that. If you have time to go back and reduce the individual fractions, you can. But she's not expecting, if your calculator doesn't do that, then it doesn't do that. You know what I mean? And with some of the bigger numbers, it won't do that.
Yeah.
Okay, so don't stress over that. Now, which one are you having issues on?
For me, it was just I was trying to see if there was like a shorter way to do it because I had so many fractions and it gave me such a big number.
What is the, okay, what part of it is it?
It's letter B on number 5.
And what is letter, hold on, what is letter B saying? Because I have to go back to, you can tell me. what it says?
It's asking for all the diamonds.
All diamonds?
Yeah,
The probability that
that it's all diamonds.
4, 3. So we're drawing 4 cards without replacement,
Yeah.
and they're all diamonds, right?
Mm-hmm.
Okay, well, how many diamonds are in the deck?
13.
13. So the first card being a diamond would be,
13 out of 52.
which is 1 out of 4, right?
Mm-hmm.
Then the next one would be what?
12 out of 51.
Which reduces by 4, I mean by 3 to 4 out of
4 out of 17.
17. Then the next one would be,
11 over 50, and that doesn't reduce.
no, and then,
And then 10 over 49, that doesn't reduce either.
and that should, it's still gonna be small, but, but that's the issue there.
So I had a question. How do I, when I look at the the question of what it's asking me, how do I know if I need to like make the fractions and add them together? Do I do it when it asks for the probability of all of them?
Okay, so generally we add when there's or, like the probability of male or female, right? And we multiply when they're and.
Okay.
There are some exceptions, but we multiply when they're and like that. So and means multiply when you're dealing with probability, and or means you're adding something.
Okay. And I meant like I know for number 5 we have to get all the fractions and like number them like what we did for king 1, the second king, and all of that.
Okay.
But we didn't have to do that for number 4, but it's kind of asking us for the same probabilities of the houses that didn't have TV. So
Okay, now you could, but the thing about doing it that way in number 4 is you're gonna have a ton of more fractions if you do that, because you have at least one there.
yeah.
And so you're gonna need the probabilities for one house, the probabilities for 2 houses, the probabilities for 3 houses. That's why it generates so many more fractions.
Okay.
Okay. Jason,
Yes.
I have to eat crow right now because I made a really elementary mistake. Let me show you what I did. And that's why she is the teacher and I am not. Let me show you what I did here. So when I went and did this, we added up, let me put it on the screen without the chat box. And let me show you what happened. So number 7, letter A, says a female student, right? Well, female students are at the bottom. I was using the wrong numerator, okay? Because I was using the males. I was using 2,534 as my numerator. And 17,230 or 320, whatever that was. But this says female, a female student. So here, this should have been, let me show you. This should have been 995. I feel embarrassed. This is embarrassing. So it's 995 divided by, what was that? 17,230, was it? Is that what it was? I think so. Let me see. There it is. I was using the males instead of the females. Okay, now if you want to reduce the fraction, you can go 900. I think this one will reduce. Let's see, 995 divided by 17,230. Okay, this is math. Convert to frac. There it is.
How do I convert?
How do you convert on the calculator? Okay, put your fraction in 995.
Uh-huh.
So 995 divided by 17,230. Okay.
Uh-huh.
And then go to the math key, which is right under alpha, right next to apps.
Uh-huh.
Go to number 1 where it has a little arrow and says frac. That means convert my fraction or reduce my fraction.
All right.
Hit enter or hit number 1 so you see this on your screen.
Okay.
Then hit enter one more time and it should reduce it for you. Now, as we discovered, thanks to Giovanna's problem, sometimes the fraction is too big for that, but most often it will reduce it for you. Okay. And so that's where it came from.
Mm.
Okay. So that was my fault. Were you able to do B on your own, or do you need my help with B as well?
No, I think I'm just gonna call it a night.
Okay. Well, I'm sorry that I led you astray on that one.
It's fine.
But good
Well,
work,
thank
both of
you.
you. And like I said, just a heads up, number 6 from 4.3, we can go over it, but if you want to get a jump start on it, there's a video up on that one, because that's a whole that's a whole explanation. Okay.
All right.
All right, we'll see you maybe tomorrow.
Yeah.
All right, Jason, thanks. Giovanna,
All
do
right.
you have a question before I leave?
No, not really. I'm on number 6 right now. I don't want to keep you long.
No, it just depends on how much are you, it's a lot of, it depends on how much explanation you need. Because how good are you at the tree diagram? The hardest part of this is the tree diagram, honestly.
Yeah, I think I know how to do the tree diagram.
This one is a bit of a, this one is a bit of a sticky one, and that's why but let me, don't quite leave me yet. I'm trying to, this is what happens when you have so many windows open. It's like, wow, I need like syndicated TV right about now. I've got all kinds of windows. I'm going to pull this up just so I can show you what I'm trying to stay ahead of everybody, and I'm not sure I succeeded, but let's see if it has. A couple of people have seen it, but I didn't know too many people that were this far into it. Oh yeah, somebody watched it. Somebody else did. Let me pull up the content so I can show you what the where is it here? Number 6. Okay, let me put this here. And I'm gonna share the screen, but I wanna pull this out first. So let me do that. Make sure I stop the screen here. Yes, I realize that I can't, I want to share you. I don't want to, okay. All right, so we're going to.
I think I did 6 wrong.
That's okay. We'll get you started. This is not an easy situation. So let me bring it up to speed here. Okay, I think I was talking about, first I was talking about making the charts, and I went through some of this first. And then I went through some of the problems. So, okay, I did this one with the juniors and the seniors. This one is up. But I also did, where's the other one that I did? Because I did another one that was, I think this is the wrong piece of video. Yeah, this is the wrong one. Let me, I did it this morning, but it's not that one. It's 4.3. I think it's under 4 points. Yeah, it's in the 4.3 homework, not the 4.2. I also did a little explanation on conditional probability. So if that is an issue, then let me see if this is where we're at. Okay, not quite. This is my, okay, I think we're getting warmer. Yeah, it's, here it is. Let me scroll forward until the whole tree diagram. So the tree diagram, take a look, looks like this. I don't know, let me make sure I'm sharing the actual video screen here. So when you do your tree diagram, it looks like this. Okay. I don't know if you've gotten that far. Oops.
I'm stuck on number 6.
This is that's the one about the students with financial aid, right?
Yeah.
So the tree diagram looks like this. Okay. Now, where did that come from? That came from, you were given the fact that there were 8,073,000 males, 10,980,000 females. If you add that total together, you get 19,053,000 students. Okay. My suggestion here, so that you don't have to convert as many percentages, is that you actually convert males and females to percentages, because everything else in the problem is given in terms of percentages.
Okay.
Okay. So when you do the males, you take 8,073,000 divided by 19,053,000. And you should get, I used 3 decimal places in my approximation here. If you use 4, you'll have a slightly different answer than I do, but it'll be close. So this is 0.424 for the male. And the complement of that, you could do it with the females by doing the same thing, or you could just take 1 minus this number to get the female. Okay.
Okay.
Are you following that part?
Yeah.
Okay. Now, the next part of this was all given in the problem. So we have people who received aid, and people who didn't receive aid. Right? So you either received aid or you didn't. So it says that 60.6% of the males received aid. So I put that on the male and aid branch.
Yeah.
And you either received aid as a male or not. So you take the complement of that, which is 0.394. Okay. You're given that of the males who received aid, that 44.8% of them received federal aid. So that's where I got this 0.448 from. And I did the complement of that to get 0.552. Any questions about that part?
No.
Okay. How about the bottom, the female part?
To get the complement, since 65% got A, to get the complement of that, you would subtract 1 from 65% and get put 34%.
34.8. And similarly for, even though we didn't end up needing this 0.49, I got it because you never know sometimes.
Mhm.
So to finish the tree, any questions about the tree?
No.
Because that tree is a project. So if you got that far, congratulations, because that was a lot of critical reading to get there. All right, now the next part of this is actually, let's answer a question.
Always does every branch.
So let me go through here, go to the next.
Can I see
Government,
number
yeah.
6?
Is that not, you mean the question?
Yeah, number 6, the question.
Sure. Let me put up the, give me a minute. Let me just stop sharing all that. You're talking about 4-3. So let me make sure I have the right homework assignment up. Otherwise, that's going to be a problem. 4-3. Okay, so here we are. We're here. That's not what I wanted. This is what I wanted. Oh, you're doing iPads. I'm sorry. I was doing number 7, wasn't I? In a box of 24 iPads, 3 are defective. If 3 are sold, find the probability that all are defective. So what's going on here is we're either defective or we're not, right?
Mm-hmm.
So what's the probability that we're defective? 1 of
3 out of 24.
Right. Okay. So again, now the likelihood that 1 is defective, assuming that, you know, they don't come from the same plant, you're going to assume that that's going to affect, because you're picking them at random, right?
Mhm.
So here, when you pick, it's just like the cards. If you pick the next one, right, you're going to assume that they have this to be, you're picking them out of the box, right?
Yeah.
So 3 out of 24 the first time,
Mhm.
then 2 out of 23, then 1 out of 21.
Yeah.
Okay. And with any luck, let me see if I can pick this up for you here.
Wait, so it would be in order 3 out of 24 and then 2 out of 23 and then 1 out of 22?
1 out of 21, right? 22, sorry, 22. Yeah, I think I said 21 the first time, but you're correct. It's 22. 4 point. See, that's why I have you and Jason around to keep me honest. Keep me from making unusual mathematical errors with my, I'm gonna send Jason the solution to that because I feel bad. Let's see, 4.3. You're on number 7, right?
Mhm. Oh, number 6.
Number, yeah, you're doing did she give us that one? Wonder if she gave you that. Did she? Cell phone. Okay, we did that. We did the TVs. We did the deck. Here's your, let me put it up. I was thinking about number 7 when I said what I said, so I have to, it is up there, but I was thinking it was number 6, but it's not. Let me share the screen so you can see what this looks like. Here's your, so here, 3 out of 24, 2 out of 23, 1 out of 22. And she just, I'm pretty sure she probably just multiplied the denominators together. Here, you get that. And this is actually divisible by 6. So we end up with this decimal, right? Be careful about this percentage. I've had students confuse this with 5%. This is 0.05%. This is really small. And generally the threshold for unlikely is 0.05. So this is extremely unlikely. Could happen, but not likely to occur.
Wait, so how do I know when I'm supposed to reduce my fractions? Because I see here that we didn't reduce.
Okay, so initially she didn't reduce it, right?
Mhm.
For the same reason that I was talking about before. So you can see what the pattern is. She did reduce it here. 1 out of 2024. So
Mhm.
if your calculator will reduce it that far, go ahead. If not,
Okay, because I reduced it, but I got a different, I reduced all the fractions and multiplied, and then I got a different answer.
oh no, okay. Well,
So
okay,
I'm
so
trying
this
to,
is
yeah.
3 out of 24 is the only fraction that reduces, right?
Yeah.
So you mean when you multiplied 1 out of 8 by 2/23 by 1 over 22, you got a different number?
Hold on, let me, maybe I got,
No,
oh, it's because I reduced it wrong.
okay,
Why?
no worries. No worries, we're all human. I proved that tonight, so.
So, okay, hold on.
Take your
Because
time.
when I put 6 over 12,144 in my calculator, I got like a totally different number.
Did you?
Yeah.
Let's see. Let's see what it is. 12,144, okay. Let's take a look. So we have, let's put it on the screen and let's see. All right, so 6 over 12,144, right?
Yeah.
Then, okay, let's go ahead and, okay, that's our exponent, right? Is 0.00049, which is going to be 0.0005. That's where she's getting that from. Okay.
Oh.
Because remember, this is scientific notation. So this is 0 point, right? Because this decimal has to move. So what's happening here is that when you see this, when you see this answer, this decimal point, because it's negative, this
Yeah.
decimal has to move 4 spaces to the left. So it moves on the other side of the 4 right here.
Mhm.
And then there are 3 zeros that we get.
Before the 4.
Yes. So you end up with 0.0, oops. Let me come down, get the mouse cursor. 0.0, oops. Come on. Are you gonna let me or not? No, you're not. Okay, fine. All right, so this is gonna be, hold on. Let me get rid of that. And let me go here. This is gonna be, oh, I see why. It doesn't want me to. I see what you're doing. It's an emulator issue. 0. Okay, so 1, 2, 3. And then it's 4, 9, 4, 0, 7, 1, 1, 4, 6, 2.
Mm-hmm.
What this represents. Okay. Now, if she rounds this to 4 decimal places, right?
Yeah.
Then this 9 behind the 4 is going to make it a 5,
Mhm.
right? So what she's going to end up with is 0.0005. So this is going to end up being 0.0005.
Mm.
And that's
And,
where,
because I got confused because for our example, we had a question similar. It was an example from 4.3. It was on number 4.
Mhm.
It was like the same that number 6 is, but we didn't do the fractions and multiply them. We did
Mhm.
P
Okay.
probability of D1 and D2, and then we did
Defective 1 and defective 2. All right,
yeah,
let's
defective one, and then put D1 in parentheses and multiplied that by the D2.
let me, are you talking about on the slides or are you talking about a homework problem?
The example
Example?
from
Okay.
yeah.
Let me pull it up and see what you're talking about so that I can look at that and see what's going on here. 4.2, you said?
4.3.
Okay, so this is share the screen, Shauna. No fair hugging, right? All right, so here's my screen. And there we go. So you said example 4, you said?
Yeah, example number 4.
Okay. All right, right here, right?
Yeah, that.
Are these 2 events independent? And no, we're not. So your question is, okay, here
Yeah, that.
2 are defective, right?
Yeah.
And so what is, I'm not sure I follow here. So you have 25 microwaves, right? We had 24, right?
Mhm.
You're selecting 2. So 2 out of 25 are defective.
Yeah.
And then since you're not replacing it, obviously, because you want to find the defective one, right?
Mhm.
You're going to have 1 out of 24.
Oh, I get it.
So
Oh,
there's,
okay. I get it. I get what we did
there's
because
the fraction.
I was confused because I only saw 2, so I thought for this one that we just did, I would have to put 2 as well. So what I did initially, since it was 3 defective out of 24, I put 3 over 24, and then I multiplied it by like 1 over 22.
Oh, you missed it.
That's what I did.
No problem. I'm glad you asked, but does that make sense?
Yeah, it makes sense.
I didn't put in this notation on the line here. I could have,
Mhm.
but I was more concerned about you understanding how the fraction went
Yeah.
initially. Like we're gonna get to that point, but most people have difficulty with the fraction themselves.
Mhm.
So I wanted to make sure you understood that that's changing and that makes them dependent.
Yeah, I get it.
Does that feel better?
Yeah.
Yeah. Okay. Anything else I can help you with?
Let's see. Are you going to make videos on the section 4.3 for like the rest of the problems, or?
Well, what is it that you, I was planning on making some more, but tell me what's giving you trouble, so I kind of know. Because we have, there's part of it for number 7 that goes with the tutoring video from, that just went up today, right?
Mhm.
Let me see, hold on, give me a minute to figure out what this is. Hold on, 4.3, you said. These problems are brain teasers. These are really, so how far have you gotten? Number 7?
Yeah, I'm on number 7.
Okay, well, we know there's help with that one, right?
Mhm.
How do you feel? Number 8 is actually an easier tree diagram to make. How are you feeling about number 8?
I'm feeling good. To be honest, I think I'll be able to handle the rest of the questions from my notes.
I think the only ones, okay, I'll give you a heads up that I was planning on doing something with number 9, because number 9 tends to, it's not long, it just tends to trick people a bit. And number 11, just because of the way the chart is worded.
Yeah.
Given one fatality at random, find each probability. So that one tends to be problematic. How
Mhm.
are you feeling about 9? Because 9 might be a little difficult. 25% of all deaths are caused by diseases of the heart. Ischemic heart disease accounts for 16.4% of all deaths, and heart failure for 2.3%. Choose one death at random. What is the probability that it is from ischemic heart disease, given that it was from heart disease? What do you think?
What is the probability? So our given would be death from heart disease, and then we're supposed to find if it was ischemic heart disease.
Yeah, you're on. So let me show you this, because this one, part of it is the way the problem's written, and part of it is it's just not written the way that you're used to. Okay, so let me show you something about this, because this one, it'll save me from having to make so I can clip this out and be like, here's the problem, folks. Let me show you this. So let me get, because this one is actually not so bad. But let me pick up the Zoom here. So the way I like to visualize this problem is this. There's different ways of doing it. There's different ways of visualizing it, but I like to visualize it this way. With what we call a Venn diagram, which you might have seen in your book. It's those things that look like a rectangle with circles inside. Okay, so I'm gonna make a couple of circles here. Okay, there's a circle here that's going to represent heart disease. Okay, and there's gonna be a circle here that's gonna represent everything other than heart disease. So I have two separate circles here first of all.
Mhm.
So here I have, now we're gonna add on to this in a second, but this is heart disease. And this is other over here. Okay. Now, in the heart disease category, you have what we call a subset. You have some sets that are inside of this.
Yeah.
So we have an ischemic heart disease, right?
Mhm.
And we have another one that's heart failure, right? Those are different, okay? But they're all heart diseases, okay? So now this circle here, that's heart disease, we know that accounts for 75% of our deaths, right? So 75% of our sample space is heart disease, yeah?
Yeah.
That means the complement of that, either it's heart disease or it's something else, is 1 minus 0.75, which is 25%, okay?
Yeah.
Now, the first part of the question, now remember this I was, this is ischemic heart disease. So I'm going to put I here. And I'm going to put heart failure here as F, just so we can distinguish this. Now, this is something that I wanted to point out with conditional probability. So here it says, choose one death at random. What is the probability that it is from ischemic heart disease, given that it was from heart disease? So ischemic heart disease, given heart disease. So in this case, you're going to have this. You're looking at the probability of, so this first, this first part of the question is, let me erase this, is going to be the probability of being from ischemic heart disease given heart disease. Okay. Well, what is, now, the reason that I like to kind of draw it like this is to show you that in this case, when we use given, that we're not thinking about the entire sample space.
Yeah.
We're thinking about just this first circle where we have heart disease. So we're looking at basically the ischemic and heart disease. We're looking at this subset of ischemic heart disease. And can you remind me what that percentage was?
It was
16.4.
16.4, yeah.
So this is 0.164, right? And I'm dividing it not by the whole sample. I'm dividing it by, given that it was heart disease, right? So here, I'm looking at the probability of, oh wait, did I reverse? Hold on. I think I'm having a bad feeling that I reversed percentages. Yeah, 25% of all deaths are, yeah, I reversed that. Let me fix that before we have another catastrophe. This, I reversed these percentages. If you go back and look, you'll see that this should be 25, not 75. So I put them in the wrong place. This is 25%. It doesn't change our mechanics, but it does change the number. This is 25%. This is 75. Okay. So now I'm going to take, to get my probability here, I'm going to take 0.164 and I'm going to divide that by the likelihood that I'm in this heart disease circle, which is 0.25.
Mhm.
And so that's where this comes from. And that percentage, I don't remember what the answer comes out to be, but let's see. 0.164. We're going to get 0.164 divided by 0.25. And this is 0.656. Okay.
Mhm.
Now, the second part of this question is, could be a little easier, could be a little harder, depending on which part of the question gave you problems. But it says, choose 2 deaths at random. What is the probability that at least one is from heart disease? Now, when
So
you
you would
have,
subtract, would you, oh, sorry.
go ahead.
I was gonna
Uh,
say at least one is from heart disease. So would that mean we would subtract one from 25%?
Now, if it were at least one, you could do that. But it says we're choosing 2 deaths. at
Oh,
random.
okay.
That's the trick. So let me show you something here, because and it's not that I wouldn't show this to somebody else, but you're working at a pretty high level. So I'm going to show you this because I think it will actually help you. And it might answer a question about why that complement formula is the way it is. Okay.
Mhm.
If it doesn't, don't worry. I just want to see if this actually clarifies anything. If
Okay.
it doesn't, we can pretend we never saw it and walk away. Okay. But if you were to think about it in terms of, here's the first death, right?
Mhm.
So it either occurs from heart disease, H, or it occurs from some other thing, right? So this is our first death, right?
Mhm.
Now, the second one, we do our little tree diagram here. And you either died from heart disease or not, just like before, okay?
Yeah.
But where I'm going with this is why the complement works the way it works. And it's easier to see it if you do this little exercise. And I know, knowing Professor Nickdell and how much she emphasizes this, I'm sure she's done it, but I want to see if maybe I can shed a little bit of light on this for you. So here, this is my second death that I chose. Now, I've got 4 possible outcomes here, right?
Mhm.
So I have heart disease and heart disease. I have heart disease and other. I have other and heart disease. Or I have other and other. Now, if I'm doing at least one from heart disease or one from other, right?
Mhm.
The reason that I can get away with that 1 minus thing, right, is because the only outcome that I'm losing is either both O's or both H's.
Yeah.
Okay. But here I don't have that luxury. This is the reason why, and the sample space helps you see it. I'm choosing not one death, but two.
Mm-hmm.
So here it says at least one from heart disease. So here I'm saying I'm using these, I'm choosing 2 deaths at random, and at least one is from heart disease, right? So I'm looking at these 3 outcomes here. Okay. And these probabilities are now, the other question that students have is, okay, so I have a 25% chance of dying from heart disease and a 75% chance of other, right?
Mm-hmm.
Now, students will ask me, well, how do I know if they're independent or not? Because heart disease runs in family, does all these things, right?
Mm-hmm.
They didn't tell us anything about the people being related to each other or anything. So we have to assume that these are as random as they're going to get. Now, if this was the same, if I said the Smith family has a history of heart disease and dad passed away from heart disease 10 years ago, right? Then I'm walking on shaky ground to call them independent in that case, because there might be risk factors that are perpetuated, but we don't have anything in the problem to indicate that. All
Yeah.
right. So you treat this in this case as if they are, this is 0.25. And this is 0.75. So these are not hard to figure out. And you don't have to do this, but like I said, I just wanted to show you here because I think it answers the question better than it illustrates it better than I could answer it for you. This is 75, right? So you pick 2 at random and the likelihood that they are at least 1. So you could do 1 minus nobody had it because you're only choosing 2 people. Okay.
Yeah.
But you could also add up the 3 products. Okay.
So I could add up.
So it would be, we want to know the likelihood. Let's go back. I'll show you right now. This is the probability. So it says, what is the probability that at least 1 is from heart disease? So that means 1 or both, right?
Yeah.
So if I look at it, I say, all right, this is, here's my little work, right? And I'm looking for, if I choose 2 deaths
Mm-hmm.
at random, what is probability that at least 1 is from heart disease? Okay. Now notice it doesn't make the same distinction that the other one did, whether it's ischemic or we don't care at this
Yeah.
point. We're just in the heart disease circle. So you don't have to, sometimes students get tripped up on that too, but I don't know what form of, it doesn't matter. Okay. So here you're doing, now what are your outcomes for this that match this? Well, you could do probability. This is going to equal, if I was going to do this the long way, because I thought this is what you were asking before. This is the probability of heart disease and heart disease plus the probability of the first one dying of heart disease and the second one dying of other, right?
Mm-hmm.
Plus the probability of the first one dying of other and the second one dying of heart disease. Okay, so you could do all 3 of these, right? add them all up. In this case, since you only have 4 outcomes, usually with at least 2, this won't work. Like if you had more than 2 people, like if you had 4 people, this wouldn't work to do it this way. But since you only have 2 people, you could just go 1 minus the probability of the thing you don't want, which is
So 1 minus, since I'm trying to look for people with heart disease, I would just do 1 minus 0.75.
square. Mhm. Try it and see. So this becomes, let's do this so that you see it. Normally that won't work, but like I said, because there's only 4 outcomes. Now, heart disease and heart disease is going to be 0.25 and 0.25, right? Then heart disease and other is going to be 0.75. Sorry, 0.25 and 0.75. And other and heart disease is going to be 0.75 and 0.25, which is the same as the last term. It's just they're in a different order. Okay. It's the same probability as the second term. So remember here, now here we're doing both. We're multiplying and adding. Do you understand why?
Yeah. Is there a way to do it without the tree diagram, or do I have to do it
No,
with the tree diagram?
you don't have to. You don't have to. I just put it up.
Yeah, because for me, the tree diagram makes it a bit more confusing.
Makes it worse. That's okay. Then, like I said, just wave goodbye to it and don't let it hit you in the butt on the way out. That's, but I figure the more times you see it, the better, because you will need to do tree diagrams on the exam. So there will be trees there. And I know that you don't have as much exposure. You probably have more because you're in the lecture, right?
Yeah.
But the students that are online are having, so yeah, if you don't want to use that, then you can ignore that part. And
So
just,
since I wouldn't use the tree diagram, would I just subtract 1 from, or subtract?
so
I would
you, go ahead.
I would subtract 1 from 0.75.
Well, be careful. How many people are you choosing?
Oh, we're choosing 2. So I would
1 minus what?
1 minus 20.25.
Okay, so, all right, if you chose to do, let me come back to you. Let's do this. Let's do this one, okay? So if you wanted to do, you want to use the complement rule, right?
Yeah.
So here you want to say, remember, we're choosing 2 people. Choose 2 people such that at least 1 died from heart disease, okay? So you're on the right track. So remember that the probability of at least 1 who died from heart disease means, in this case, it means 1 minus the probability. Now, the only other thing that you don't have in this case, right? If at least 1 died from heart disease, that's 1 or both, right?
Yeah.
So the only thing you don't have is that no one died from heart disease. Would you agree with that? So now this is, here's where you're getting tripped up. It's 1 minus, we know that, right?
Yeah.
How many people die?
How many people that 25?
No, how many people die?
Oh, how
Two.
many people?
2 people, right? You're
Two
choosing
people
2
die.
people who die, right?
Mhm.
Now, okay, so now these people did not die from heart disease.
Mm-hmm.
No one died from heart disease. So what is the probability that you did not die from heart disease?
75%?
Yeah, this is 75 because if you do the minus, right? You're
Yeah.
doing the people who died from something else.
Yeah.
Okay, so that's the hard part to remember. It's the opposite group.
Mhm.
Okay, so this is, or the complementary group, I guess I should say. Now, the likelihood that you died from something else is 75%.
Yeah.
So this becomes this answer. And yes, you can use a power. I purposely didn't because I wanted you to remember that there were 2 people here.
Mhm.
So
Okay,
that,
so since it's not one person, since it's 2 people, it would be 2 75s.
yes,
Okay.
because remember their probability is independent, right?
Yeah.
We're assuming for the sake of this example. That was where you kept mixing up the percentages and you were only choosing one person. I needed you to see that the answer comes out to, let me see here, 1 minus, see if I can operate my calculator. This comes out to 0.4375. Okay. So whichever way you choose to do it, that will work. Okay.
Okay.
But that one tends to trip people up. So I'm going to leave it there. If there's anything specific that you do get stuck on, drop me an email message or drop me a message in the Canvas or the chat.
Okay.
And I'll be glad to, we do have another meeting tomorrow. So if you're able to come on Friday, you can come and jam with us. We always enjoy having you.
Okay.
But that tends to be one of the problems that people tend to get stuck on. So
Okay. Well, thank you for the help.
you're welcome. Thank you for stopping by. And we'll see you again soon. Okay.
Okay.
Take care.
Thank you.
Bye now.